Okay, so we know about joint probability distributions, discrete probability distributions, continuous probability distributions. But anyone remember what was the first topic that we covered in class? What was the first thing we started with? The mean and the variance, right? So we started discussing those concepts, and we applied those concepts to a sample space and also to experiments. So we were able to compute the mean, the variance, the median, and so on. Now, what we're going to do is, now we know the concept of a random variable. We know the concept of probability distributions. So we're going to use those mean and variance, median concepts. We're going to apply them to random variables. Okay? So this topic is about the mathematical expectation, which is the mean, or how we call the mean for a random variable. Okay? So we're going to use some of the concepts that we learned at the beginning of the course. We're going to apply them to the concept of a random variable. So this class is about mathematical expectation. And essentially, the topics that we're going to cover are how to get the mean of a random variable, how to get the variance and covariance of random variables. So the objectives or the learning objectives, what I want you to get from this lecture is how to calculate the means and variances for a random variable. Okay? So one thing that you need to be clear is for this chapter, I'm only taking those two subjects because I believe those are the ones that you're going to be needing from this class. So when you go read the book, just focus on those two topics, okay? You're going to see more material in the book, but just focus on the mean and the variance and covariance for random variables, okay? So let's start with what I just said. So we know in lecture 1 we discussed how to get the sample mean. Now let's consider the following. So let's go back to this example in which you have 2 coins and you're tossing that coin 60 times, or those 2 coins 60 times. And x is your random variable, is the number of heads that occurs per toss. So you're giving a value of 0, 1 to this x random variable. So let's say that the values you get is 0, 1, or 2, meaning that you have no head, 1 head, or 2 heads. Okay? So suppose that the experiment yields no heads, 1 head, and 2 heads with these amounts. So you have 4 no heads, 7, 1 head, and 5 times you get 2 heads. So now we want to get what is the average or the mean for this experiment. Any idea? So you're not just looking at the number twice, you're also looking at the value of the random variable. So if you look at this, you have 4 times, oops, so I guess the answer is there, but I was not intending to do that, so let me write this really quick. So you have 4 times 0, you have 7 times 1, and you have 5 times 2. Those were the outcomes for your experiment. So if you divide that by the number of tries, that will give you 1.06. So as you can see, what we just did for the discrete random variable is how you compute the mean or the expected value. Okay? So another way to see it is by looking at the value of the random variable and multiply that by the probability or the chance to get that outcome or that value for the random value. Yes? Yes, it's a weighted sum. So we look at the outcome of the random variable and we multiply that by the probability of getting that outcome. So as you can see, this result is not one of the outcomes of your experiment. You're getting 1.06, but that is the mean. Okay? So the mean is not necessarily one of your outcomes. This is basically telling you that you have almost the mean or the average that you're going to get is close or a little bit higher than 1. So this is an average value of the data, and that is not a possible outcome of your experiment. And we're going to revisit this problem in a few minutes. So just keep in mind, we're trying to calculate the sample or the mean of random variables. Okay? Not the sample. We are looking at the random variable itself, the value of the outcomes of your experiment. Okay? So we shall refer to this average value as the mean of the random variable x, or the mean of the probability distribution of x. And the way we're going to represent these, that is different. You remember the symbol that we used to represent the mean was x bar, right? Now, to differentiate between that and the mean of the random variable, we're going to use mu x, or simply mu when it's clear that we're referring to a specific random variable. Okay, so when you see mu, that means that you're looking at the mean of a random variable. It is also common to call this being the mathematical expectation, or the expected value of the random variable. When we mention the expected value, we also use E of x. So E of x is referring to the expected value, which is also the same as the mean of the random variable. Okay, so I'm going to use expected value, mean of random variable, is the same concept. Okay, it's the same thing. Okay, so from here, let's revisit this problem. So this is tossing the coin again. So assuming that we have one pair of coins, so it's the same probability of getting a head or a tail, was tossed twice, so you're throwing that coin twice, and we find that the sample space for our experiment is this. And we know that. We know how to get that sample space. So the only options you have is to get two tails, two heads, one tail, one tail, one tail, one head. Okay? So since these 4 sample points are all equally likely, it follows that the probability of getting 0 or getting 2 tails equals 1/4, and the probability of getting 1, if you sum them, equals 1/2. Because each outcome of your experiment has the same probability. Okay? So we have also the probability of x equals 2 is going to be 1/4. So each outcome from your sample space has a probability of 1/4 or 0.25. So when you add those 4 outcomes, you get the total probability, which is 1. So therefore, you can get the mean of the random variable, or the expected value for the random variable, by looking at the outcome times the probability, plus the outcome times the probability, plus the outcome times the probability. And that equals 1. Okay? So this result means that the person who tosses 2 coins over and over again, on the average, should get 1 head per coin. Okay? Which makes sense, right? Just we have a equally balanced coin. Okay? So now that we provided some examples, this is the definition. So we are looking at the random variable x with the probability distribution f of x, and the mean or the expected value for this random variable is given by this expression, which is what we did. The summation of the value of x times the probability of that outcome. And that's for the discrete case. Now, for the continuous case, guess what? Instead of looking at the summation, what you do, you look at what? The integral. Okay, so you integrate the value of the random variable times the probability. And the probability is given by the density function. Any questions? Okay. So in the mathematical expectation, the expected value is calculated using the probability distribution, which is this value f of x. Okay, so the probability distribution, again, is defined by the function in the continuous case, or the in the probability density function. And also, you can use a table to define it for a discrete case. Okay, so let's work with this problem. So here we have a lot containing 7 components, and is sampled by a quality inspector. The lot contains 4 good components and 3 defective components, and a sample of 3 is taken by the inspector. And I ask you, find the expected value of the number of good components in this sample. So what would be the first thing you will do? Remember, we need 2 things. We need the value of the outcome, which is our random variable, and we need the probability, which is f of x, right? So I think we know what the values are. The only thing we don't have is the probability distribution. So any idea how to get that probability distribution? And this is something you know. I mean, you already did that for other problem in class. Right. So that's the idea. You need to define your function, your probability function, using the, just stated here. First, let me state the random variable. So we're going to use x, and x is the number of good components. In the sample. Okay, so let's define f of x. And we are looking at the probability of an event happening. Okay, so we want to find the expected value of the number of good components in this example. So x is the number of good components. So you need to choose from 4 components that are good, x components. And you're going to multiply that times the 3 components that are defective. And that is divided by 7, and you have to choose 3. So that's the number of options that you have. That expression is going to give you the probability for x. So you want to know what is the probability of getting only one good component? You plug x there, you'll get that probability. Same thing for 2 and 3 and 0. Okay, so this is valid for x equals 0, 1, 2, and 3. So if you solve for 0, this is 1 over 35. For 1, this is 12 over 35. For 2, this is 18 over 35. And for 3, this is 4 over 35. Yes, because you're taking 3. That's the size of your sample. So sample of 3 is 8. Okay, so you have to limit that up to 3. Any other question? Okay, so remember, in order to get the yes, sir.
Why do you say 3 minus x again?
Because if you choose 1, that is non-defective, that means that you're going to have 3 minus 1 defective.
Okay, you choose one that's not.
Non-defective, then you're choosing, you're having 1 minus that.
Okay, with the.
Yes.
But if it's random, I'm assuming, then how do we know it's non-defective?
Yes, because this is the probability of getting one that is non-defective, right? And the only possibility that you have is going from 0 to 3, because you are choosing only 3 from the sample. Okay, so that will give you the probability, and we need that probability because we are.
I see. We're actually spacing it. The x could be 0, 1.
Exactly. So now we want to find the expected value. Okay. So the expected value is going to consider all those probabilities and all the outcomes. So mu, is this a continuous or discrete random variable? Discrete, right? So we look at the summation. So mu is going to be equal to 0, which is the first outcome, times the probability of 0, plus 1 times the probability of 1, plus 2 times the probability of 2, plus 3 times the probability of 3. So this is 0, and you will get 12 over 7, which is 1.7. So this is the expected value for that random variable. Let's look at one problem in which you have to look at the continuous case. So again, this is discrete. Now let's look at the continuous case. Okay, so let x be the random variable that denotes the life in hours of a certain electronic device. The probability density function is given by f of x. So that's the density function for the life in hours for this device. And I want you to find the expected life of this device. Any idea? So what we did for the discrete case, we look at the summation. For the continuous, we look at the integral, right? This integral is going to be defined for x being greater than 100. So we go from 100 to infinity. We know the density function. What is missing? In addition to the answer? Right. So we need to multiply the density function times x. You know why? You need to know the outcome of the random variable times the probability. Okay? Just like we did for the discrete case, we need to do that for the continuous. So this x is giving you the outcome of the random variable, and the function is giving you the probability, f of x. Okay, so you need to multiply that times x. If you solve this, you get 100 times infinity, 20,000 divided by x cubed dx. It should be square. I'm sorry, this is square. You cancel x. Yes, you cancel x, so you get square. And then you solve this. This is 20,000 times negative 1 over x. So this equals minus, this is 0, minus 20,000 over 100. So this is 200. So when you substitute the infinity here, that goes to 0. This goes to 0, and then you get this expression, which equals 200. Questions? Okay, so now you have 5 minutes to solve this problem, right, on your own, on a piece of paper. And if you submit it and it's right, you get 1 point, bonus point for the next exam. So you need to work on it on your own. And you cannot use the textbook. No, the textbook. This is a problem from the textbook. So you need to close the textbook.
Me and our neighbor.
No, you have to work on your own. So one hint, you need to find the 4 outcomes. There's 4 outcomes for this problem. Just find those 4 outcomes and find the mean. So what are the 4 things that can happen? You get 0 because both of them rejected your offer. You can get one of the contracts. Those are 2 different outcomes, and you can get both of them. That's another separate outcome. It's just like the toes of a coin. You can get 0, you can get 1 and 1, or 2. So if you know the values for the outcomes, for each outcome, for the first one, what would be the value? For the second one? 1,000. For the second one, for the third one, exactly. So one outcome, 0, because you don't get any of the contracts. Second outcome, you get one of the contracts. Third outcome, you get the other contract. Fourth outcome, you get the 2 contracts. So if you add those 2 amounts for each outcome and multiply times the probability, you should get the expectation. That's what I want you to do. What is the probability of getting 0? You have 70% chance of getting the first one, 40% chance of getting the second one. So if you don't get any of the two, what will be the probability?
90%.
No. Is the complement of those two probabilities multiplied? Right? There's two independent events. You look at the probability of not getting any of the two, you multiply them, you get the probability of not getting any of them. Just like the secret, remember? Correct. Just put your name on it. So on your paper, just put your name, and I'll give you 1 more minute to finish and pass it to that side of the classroom. Okay, so pass your papers. Pass whatever you have. Put your name, remember to read it.
Yeah.
Any other papers? Any other papers? Okay, so I'm in a good mood today. So if you try it, I'll give you a point. If you got it right, I'll give you 2 points for the next sem. Okay. So if you try it, there's a bonus for you. Okay. So let's work on this problem. So as I mentioned already, we need to look at the 4 outcomes. Okay. So we have 4 possible outcomes. Those are 0, 1,000, 1,500, and 2,500. Okay? What would be the probability of getting 0? Correct. So you have 1 minus 0.7 times 1 minus 0.4. So that's equal to 18, right? So for 1, actually 1,000, you have the probability is 0.7 times 1 minus 0.4, and that equals 0.42. Then you have for 1,500, excuse me, you get 1 minus 0.7 times 0.4. This is 0.12. And then for 2,500, this is 0.7 times 0.4. And this is 0.28. Okay, so that's what I was trying to explain to you. So you're going to get the distribution. Those are the probabilities for each outcome. You know the outcome for each probability. So the expectation equals 0 times 0.18 plus 1,000 times 0.42 plus 1,500 times 0.12 plus 2,500 times 0.28, and that equals 1,300. How many of you got it right?
If I didn't write it as a count, I'm pretty sure I still got it on calculator.
Okay, so
Yeah.
at least now you understand. Okay, so we get the expectation. We look at the outcomes. So in that case, you have 4 outcomes, which are the totals of the money you get, times the probability for each outcome. Any questions? No questions. Okay. So now we're gonna look at different cases of the expectation. So for now, we're just looking at the value of the outcome as x, but we can also have a different way to express this outcome. That could be a function, for instance. Okay, so instead of having x or f of x times x, like we did here, here we have the function, the negative function times x. This outcome can be defined also by a function. Let's say 2x or 2x minus 1. Okay? So that's the type of problem you need to understand as well. Okay? So the outcome, but you can also have a function to define the value of the outcome. And that's this case. So now we're going to consider a new random variable, which is given by g of x, which depends on x. For instance, we can have x squared of 3x minus 1. And what we're going to do is to find the expected value of that random variable, g of x. And instead of looking at x here, now we're going to evaluate the function with the value of x, and we're going to multiply that by the probability of that event. Okay? Same thing here. Instead of looking at the summation, we look at the integral for the continuous case. Okay? And I believe this is going to become more clear now with the example. But again, let's say you want to know this function can define 3x minus 1, the money you get by serving a customer. Okay? So let's say you get $12 for each customer you serve, and you want to get the expectation of knowing that outcome. So if you serve one customer, you get $12, you get that value, or the value of that function is 12. If you serve 2 customers, the function is going to be 24, and so on. Okay? So that's the type of problem we look at with this concept. So this is an example. Here in particular, we're looking at the car wash. So suppose that the number of cars That's our random variable x that passed through a car wash between 4 and 5 in this hour. And any sunny Friday has the following probability. So we have the probabilities, and those probabilities are given in this table. So what type of distributions we have here? This is a discrete distribution. So for x equals 4, we have this probability, and for x equals 9, we have this probability. Now we have a function to define g of x, which is equal to 2 times the random variable minus 1. And that represents the amount of money in dollars paid to the attendant by the manager. We want to find the attendant's expected earning for this particular time period. Okay? So we're going to use this function. We're going to evaluate those random variables using this function, and we're going to find the expected value. Okay? Are we clear? What we want to do in this problem? Okay, so now we are not just looking at the outcome itself, we're going to evaluate that outcome with a function, g of x. Okay, so by the theorem 4.1, we know that this expected value of g of x is going to be equal to the expected value of 2x minus 1. And that will be equal to the summation, because this is a discrete random variable, from x equals 4 to x equals 9. The function g of x, which is 2x minus 1 times the probability. And in this case, that probability is coming from this table, which is very simple. So we can solve this by looking at the value. What will be the value for x equals 4? So if you put x equals 4 in this function, what do you get? 7. 2 times 4 minus 1, 7. So you get 7. And what is the probability? 1 over 12. Plus, now you have to evaluate 5. This is 9 times 1 over 12. Plus, you evaluate 6. This is 11 times 1/4. Plus 13 times 1/4 plus 15 times 1 over 6 plus 17 times 1 over 6, right? And that expected value equals 12.67. Okay, so don't get confused. When you solve this, you get 7. That doesn't mean that you have to go here and find 7. Because the random value or the random variable value is 4. That's the value of x. Just evaluate x equals 4 in this function. But x is still 4. So you use the probability of 4 times the value of the output. And the same thing for the other outputs. Okay? So that tells you that this is the earnings of this person for that hour. Okay? So working for a car wash, you get $13 an hour. Not that bad, right? Let's look at one more example, and then this is the last example we're going to work today. So let's look at the case in which we have a continuous distribution. So what do? We have a random variable with the density function that is given, and we have g of x equals 4x plus 3. So we use the same definition, right? But instead of using the summation, now we look at the integral. So e of this. So the expected value of that function. What are the integrals limits? -1 to 2, correct. G of x is 4x plus 3. What is the value of f of x? Right, it's the distribution that is given, the density function. So you need to multiply this function times f of x dx. I'm sorry. So that's the expression you need to solve. So this will become 1/3 times -1 to 2, 4x cubed plus 3x squared dx, and the integral should be equal to 8. So same concept, this is easier to solve. Instead of looking at each outcome, just multiply and integrate. Yes, sir. X squared, where? Here? Yeah. So you have, yes, so you have 1/3 outside. Yeah, so they won't cancel. Yes. That's why I have this. Any other question? Okay, so today we look at several things, but the main topic is the expectation of a random variable. We're looking at the mean of a random variable. Okay, so that's what we're trying to do. We know about random variables, now we're looking at the mean. Next time, on Wednesday, we're going to look at the values. Okay, so please look at this, refresh, review, because next time things are going to get more complicated, okay? Remember the homework? Homework is due on Wednesday, and I'm going to be in my office this afternoon and tomorrow and Wednesday afternoon. So if you have questions, please come back. Yes.
I got the right answer initially, or did I change? I was trying to figure out why I got the right answer because I used a completely different method.
Just 1 second.